good evening, dear ladies and gentlemen. I warmly welcome all of you who are joining today's webinar from Sri Lanka and other parts of the world. The conference webinar series is hosted by the University of Peradeniya as a part of its international research sessions iPURSE, scheduled to be held on the 19th and 20th of August 2021, and is organized by the iPURSE committee together with the International Relations Office of University of Peradeniya. So this is the fifth pre-conference webinar titled One Health and Nature-Based Solutions. Let me introduce the moderator of the webinar today, Professor Rupika Rajakaruna from the Department of Zoology, Faculty of Science, University of Peradeniya. Professor Rupika Rajakaruna is the Chair Professor of Applied Zoology. She is an eminent researcher in the field of parasitology with a special interest in the area of vector-borne zoonotic diseases and disease ecology, and has authored more than 90 research publications in local and international peer-reviewed journals. With this very brief introduction, I kindly invite Professor Rupika Rajakaruna to start the proceedings of today's webinar titled One Health and Nature-Based Solutions. Over to you, Madam.
Thank you, Professor Karunaratne, for that kind introduction. Good afternoon to the Sri Lankan participants, and good morning and good evening, whichever applies to those who are joining, connecting globally. So once again, let me welcome all of you to the pre-conference webinar on One Health and Nature-Based Solutions. So One Health is a collaborative, multi-sectoral and transdisciplinary approach working at the local, regional, national, and global levels. So this concept recognizes that the health of people is closely connected or associated to the health of animals, plants, and our shared environment. So the concept of One Health is not new. So it has become more important in recent years and is gaining recognition globally. So it involves experts across a wide range of disciplines and sectors in monitoring and controlling public health threats, and is an effective way to fight issues at the human-animal environment interface, including zoonotic diseases. So the best example that we can take is the current pandemic that we are all experiencing. So we are holding this online because of that. And we all know, although we all know that the virus, the COVID-19 virus, the origin is from bats. How it came to human is still a mystery. So people are working on it. So this is a best One Health example that you can think of right at the moment. So today we have two eminently qualified speakers, Dr. Ananda Malvathandri and Professor Suzanne Lenhart. And the two topics that they will be dealing are maintaining nature-based solutions for sustainable development and resilience by Dr. Ananda Malvathandri, and then One Health, connecting humans, animals, and the environment, but by Professor Suzanne Lenhart. So before I introduce the speaker, the first speaker, let me go through some of the housekeeping items here. So I invite you to utilize the chat box or the Q&A to post your questions, and we will dedicate some time at the end of the presentation once both speakers have made their presentations. So, let me introduce the first speaker, Dr. Ananda Malvathandri, who is currently the country representative of International Union for Conservation of Nature, the IUCN in Sri Lanka. Dr. Malvathandri holds a BSc in chemistry and a diploma in business administration from the University of Colombo. He received his doctorate in soil physics from the Washington State University, Pullman, USA, and his MSc in environmental science from the same university as a Fulbright Fellow. So before joining the IUCN, he served at the UNDP as the Assistant Resident Representative for Environment Sustainability and Disaster Resilience in Sri Lanka, and as a Senior Advisor and Director for Energy and Environment for USAID Colombo. So Dr. Malvathandri serves in many voluntary positions, such as the Ceylon Chamber of Commerce, Biodiversity Sri Lanka, National Science Foundation, the Association for the Disaster Risk Management Professionals, are to name few. Today, we really appreciate your time and your effort in making this presentation, Dr. Malawatantri. His topic is, once again, mainstreaming nature-based solutions for sustainable development and resilience. So, Dr. Malawatantri, over to you, sir.
Thank you, madam. Thank you for the wonderful introduction. And first of all, I'd like to thank Professor Inoka Karunaratne for inviting us and the whole iPURSE team. To start with, I'm really delighted to be part of this process. It's especially since it's a multi-stakeholder, multi-sector platform. I think I really like the approach, because the talk I'm going to deliver today requires that kind of a multi-stakeholder thinking. So first, Professor Rupika Rajakaruna, and I'm not too sure the Professor Lenhart is still here, and all the distinguished participants, ladies and gentlemen. So let me share a few of my slides. If I can grab the screen. Thank you very much. Hopefully you can see the slides now.
Yes.
All right, thank you so much. So basically what I will do today is to walk through a few key areas, because nature-based solutions is a very vast area and picking up fast. And there are a lot of interest, especially since COVID. So what I will probably try to improve our understanding of nature-based solutions, especially to address the societal challenges we are facing today, not only the ecosystem management, and also the elements in the nature-based solutions and the importance of science-based approaches. When I say science, social science included, because we need a solid, good tracking systems and monitoring systems to for the success of nature-based solutions mainstreaming, which I'll try to articulate why. And then I'll probably highlight a few examples. Some are from Sri Lanka, some are from other countries. And also probably we'll discuss a little bit on the basic building blocks that are required to implement and mainstream the nature-based solutions, such as the economics and the sustainable financing. So in this context, now the context we are sitting in today, I believe, especially the university, we have a lot of opportunities and challenges as well to take the nature-based solutions and do a lot of research and support the country as well as the region and the world by bringing more research and evidence-based thinking, so that the applications of nature-based solutions become more and more it's relevant, and also will help the adaptive management of to address the current challenges we are facing today. So normally, we used to think conservation and development as two things. That had been probably one of the biggest mistakes we did in the past, because we always say development is bad. But we don't talk much about how to do the development in a sustainable and resilient manner. So the nature-based solutions is one of those bridging things that will allow us to start thinking we could save the ecosystems for our future generations while having the systems in place so that the development can progress, people can increase the quality of life, the health quality included, and also address the situations like the poverty, the climate challenges, etc. So basically, the nature-based solutions encompass many topics that we used to work. We used to say ecosystem-based disaster risk reduction, ecosystem-based climate adaptation. So many things were brought in as a one umbrella system under this nature-based solution. So as a result, nature-based solutions is a framework. It's not the means to end, but it's a good framework that will get us working together in the context of sustainability and resilience. So that's probably the universities and the academics and the research has a lot to play to ensure that we benefit directly from these kind of approaches and adapt it into our beautiful country, which is a biodiversity rich place. It's an island. So we have all the basic building blocks, but we need the evidence-based thinking to go. So one of the things we often talk about this increasing disasters, the increasing trend. We tend to attribute all these things to climate change. Increasing drought is climate change, increasing flood is drought change, landslide climate change, storm frequencies, the velocities are related to climate change. Now, we have another element comes in, that's the ecosystem, because all these disasters also disturb the ecosystem services and the ecosystem. So now the nature-based solutions allow us to put the, because it's a catch-22. If you climate change destroy the ecosystem, when the ecosystem is not healthy, you feel the climate change more and more. So we will see some of the examples coming up very soon. So what are we aiming at? We are aiming at a situation, we need a just world, everybody included, in a changing climate. We have a lot of expectations. We have the whole social foundation to work with, the energy, jobs, resilience, education, income, water, access to water, good quality water, food security. And then on the other hand, we have disaster risk. And then we have opportunity to think broad and bring technologies and change our perceptions, the way we are thinking towards it. Because now we had this, I think over the years, we had this, what do you call this, silos thinking. Simply one agency goes and do certain things and don't talk to the other agency, then you come and wipe out the development by the other, you know what I mean. But I think the nature-based solutions will provide us a good framework for inclusive and sustainable economic development, where the university research, the good work can be supported for the planning processes. So there are a lot of new concepts are emerging now. The internet is now full with circularity needs. How do you work on cradle to grave? You have a product and then you make sure that you try to do the recycling, the reusing, and at the end you probably recover a little bit of energy, but don't do it without trying the full recycling aspects, sustainable and consumption and production, and doing away with dirty power sources like coal and oil. Now, the COVID has put a lot of new thinking now. For example, the European Union, now their tax schemes is having conditions on products coming into Europe, starting probably next year. If any garment or any product going out of a country, you will have to mention how much of that product consists of non-renewable resource energy supplies. Then whether that facility was located in a polluting environment. Earlier, we used to talk about the number of toilets for the workers, the benefits for the workers, the child labor. Now we are getting into the ecosystem. Now people are asking Are you using science-based targeting? Are you doing life cycle analysis? All kind of new thinking is coming, and I think it's a paradise for the universities to get into these areas and work on the science, sociology, economics, and all that. So when it comes to the nature-based solutions, there are plenty of playing fields. I know most of you are working on these different areas. You have the wetlands, the fisheries, the coastal and marine, then the typical situation and the water conveyance, especially a country like Sri Lanka, which we'll talk a little bit more in the next slide. And then the carbon sequestration, coastal defense, having mangroves to defend us from storms and sea surges. And then, so it's, you can see water has a real connection with the water quality and the quantity, both in nature-based solutions. That's one observation, but there are many observations that one can make. So IUCN, International Union for Conservation of Nature, is taking a huge leadership in the promoting nature-based solutions. And now the many agencies are now coming together and working now working together. Actually, we had last week, we had an announcement in Sri Lanka, the World Bank, IUCN, UNDP, another entity, it's a Korean entity called Global, I can't remember, it's GGGI. It's an initiative on the low carbon. So to work together to help Sri Lanka. Basically what nature-based solutions advocate is you safeguard the nature so that nature will provide better ecosystem services. That will safeguard the society. So we work on that paradigm. And then it will allow us to address most of the social issues from poverty to many other equity issues and the rights, all that. So that's why it is a good conservation and science combined platform for us to work. And it's very rich, and there's a lot of room for anyone to work in this framework. Now, for example, the societal challenges that can be addressed with nature-based solutions, which is very relevant for the today's conversation. Nature-based solutions can be the entry points for climate change mitigation and adaptation, disaster risk reduction, economic and social development, human health, food security, water security, reducing the biodiversity loss. So that really takes everybody's attention to this framework. So the definition, the theoretical definition provided by IUCN for the nature-based solution is actions to protect, sustainably manage, and restore natural or modified ecosystems that address societal changes effectively and adaptively, simultaneously providing human well-being and biodiversity benefits. It's not only one side. It provides human well-being while conserving the biodiversity, which will come back and help the human well-being. So it's a circular path, and that's, I think, the Sri Lanka, we have been, our ancient kings have been doing this, so that's the beauty of it. We are revisiting nature-based solutions in a different lens now. Now, there are a couple of associated terms with nature-based solutions. One we call it the nature-derived solutions. Now, the wind is one. Now, for example, if you take Sri Lanka, we have more than 5,000 megawatts of wind power, not ready to be developed in a very easily accessible places in the coastal areas as well as in central hills. Now, if somebody wants to do research, you could very easily convert Sri Lanka into a hydrogen economy. With hydrogen now, Germany, you have trains running, buses running in Aberdeen, Ireland. So the people are picking hydrogen as a source to store energy generated from renewables. So you don't have to go and connect to the grid. But these require a lot of research, a lot of changes in the way we think. But if you do, in Sri Lanka, the total demand is around 3,500 megawatts. We have about over 5,000 undeveloped capacity in wind. So that tells the story. The oil-dependent nation can be total renewable if you go in that way and do the right research and do the right economic analysis and go and do the sustainable financing accordingly. The nature is inspired solutions. That means you borrow from nature and try to mimic. Now we see green buildings coming up. We see the plants being used inside to minimize the air temperature inside. So your air condition load is coming down. You could have parks around the buildings, more trees around the buildings. So again, the total air conditioning load coming down. But to convince this, you need research, you need numbers, you need advocacy, you need good communications that include the perceptions. Nature-based solutions is a straight one and the one we understand most and where most of the examples are also from. So use the nature to try to minimize the disasters, you try to do it economically and all that. So in the systems thinking related to nature-based solutions, now this graphic is a really good one to explain it. So the level of complexity and the level of transformation of the existing ecosystem. The lowest transformation is you maintain the existing ecosystem and use the services from natural ecosystems. Why it is more complex? The knowledge. Because to understand the nature, you need special knowledge. You need to understand the climate processes, soils processes, water-related processes, and the people's thinking, traditional knowledge, and all these things come. So a lot of modeling, a lot of thinking going on. So no, Peradeniya, you have pioneers in this area. So then you have in the middle the manage and restore the ecosystem. So first you keep what you have, then you have the degraded lands and things like that. You bring the restoration in between and then restore the ecosystem to deliver the same ecosystem services that are given by the natural ecosystem. So in that case, you could bring engineering, you could mix a little bit of concrete among the vegetation and then come somewhere in the middle. It's less complex because you are in control and the ecosystem transformation or the change you have incurred is a little bit more than what you have seen in the natural ecosystem. Then the last one, the creation of a novel ecosystem, basically it's almost like making a robot. You just create a novel ecosystem. Now take greenhouse agriculture. It's a novel ecosystem. It's not complex. You know what the nutrients you are giving in, you know what is going to grow, you know the output also before it comes out. So the bank is more reliable and bank has no problem in giving money. So these are the thinking. It's not difficult to understand, but we need to understand the training, the capacity building, and the research needs when you deal with these kind of systems. So the complexity reduced with the enhanced management. That's where the science go. And then the hybrid systems, green and engineering coupled, are sometimes needed to meet the major challenges because you cannot simply do everything by greening. You need a little bit of a modern knowledge mixed with the traditional knowledge, mixed with the ecosystem knowledge so that you can meet the climate change, food security, and disaster risk reduction. So these are some of the examples. So you could design the conveying water. Earlier we had these normal channels dug in soil. You could just develop it. Then you can, the one on the right side below, you could have the elephants walk across it, but still you carry the water. So these are simple, very simple things. And then this is an example from New York City. Now, New York City recently ran out of stormwater handling capacity. They couldn't cope up with the load in the Hudson Bay. The whole water coming from rain and draining into, so to make a real mess. So they decided to use the nature-based solutions and then take the water from the roadside and then start growing trees in the middle of the city. So these are examples from New York City. And then they have engineering designs, different layers of soil, different layers of gravel or metal. So then you use geotextiles. So I remember once seeing the Haley's geotextiles in Chesapeake Bay, southern New York. They were using Sri Lankan geotextile fabric in some of those designs. So when it comes to the theoretical framework, you need to start having a holistic view with the science, the practice, and the policy all taken together. So that's why the universities have a huge role to play and to work side by side with the private sector and work with the government so that you bring this knowledge to different parties and even to the communities. Because sometimes we think that the community is totally capable of understanding, but sometimes you need very innovative approaches to bring that to the practice. So you have the science, you have the practice, you have the policy, and then the implementation, you can think many examples. Mangrove restoration, the slope stabilizations to prevent landslides, wind barriers. We will talk some of the examples in a while, and evaporation control. So there are a lot of things that now we talked about the soil organic improvements. These days, a big hot topic. I know a lot of people in Peradeniya are actively involved, trying to convince why it is required to take a little bit longer time than changing overnight. So these are the kind of things that we need nature-based solutions articulate properly so that the whole part is the policy and the practice will come together. Now, these are some of the examples. I will show a few examples. These are the Central Hills with the Knuckles, Horton Plains, where the river starts. We have the situation that the plantations and the land degradation has taken toll on the ecosystem. You need the nature recovered and restored because then only the cloud capture occur. Because for cloud capturing, you need the tree cover. Then once you have the tree cover, you are resistant to the high intense rainfalls. So your erosion is less. And then the infiltration of water slowly seeping into the groundwater without straight away going to the stream and going into the ocean is less. So when you have reduced erosion, now we know our reservoirs are getting filled quickly because of the high erosion rates. When that happens, the water availability for irrigation, agriculture, drinking, urban services, and power generation is less. And also it affects directly to the droughts and also to the floods. So then nature-based solutions has a lot of examples to make sure that the reservoirs will be filled. The water regulation, the time of arrival of the water is regulated so that you don't have floods. And it is same for the urban situations as well. Now, when you look at around the world, now you can see where the nature-based solutions are being captured. This is the NBS policy platform did this study. You can see most of the nature-based solutions have been applied to terrestrial forest and woodlands naturally. Then comes the coastal areas. Then you have the catchments. Then you have the agriculture. Then you have the grassland, rangeland, and then mountain habitats. So you can see the high applicability in the terrestrial forest, but these are also changing. Now, these are some of the pictures that we are familiar. These pretty much, these are some of the selected ecosystems where we have. Another part of understanding and implementing the nature-based solutions is a detailed understanding of the processes knowledge. Now, it's a simple example I will be using is the erosion. Now in the erosion, how the erosion occur? Erosion occurs when the higher intensity rainfall touches the surface, the soil particle get detached. Then it goes transporting and it either deposits or it get into a river like this. So that's why the Ambatale water treatment plant getting a lot of silt. Now we estimated the amount of silt in the Callan River for 5-year modeling. It gives us about 2,800 tons of silt in the Callan River passing Hangala Bridge every year. So these mechanisms are required because why? Then only you can talk about the cover, whether you are going to mulch it, you got to plant the trees and do whatever to minimize this kind of dislodging. Same with the wind erosion. This water, this wind. We call it, this the transport, we call it the siltation. It just keeps jumping. The smaller particles jump over the surface and the other suspensions will go up and go like clouds. So if you have been in Middle East, you know what the cloud look like. So there are a lot of nature-based solutions. I showed the New York example. Once there are many things that the engineering can do. And I know Professor Ranjit Disanayak and colleagues in Peradeniya are doing these kind of designs, and we need more and more. And these are not just beautification of city. They are groundwater recharge, taking the chemicals out of the vehicle, chemicals leaking from vehicles and also in the runoff, so that our groundwater will be a little bit better and all that. So these needed more research and more economic calculations why we should put money into these kind of things. And also the cross-pollination of cross investments between sectors. Now, with the tourism benefits by having a beautiful area. So there should be a discussion between the tourism and the urban planning and the research. So there are more examples, mixing the green knowledge. This part of the human-elephant conflict designs IUCN did in Yarnoya. So you need a lot of scientific data. Now this, what you see on the bottom is the tracked images of elephants moving. So with that, you can create this kind of, so you bring the new technology and the traditional knowledge and then come up with hybrid options to help continue the development process. At the same time, you safeguard the lives of the species. This is another example from Italy. It's a constructed wetland. We have tons of wetlands around us, but this one takes the city water and purify it before draining into one of their main rivers. So the economic calculations have proved that having this wetland, the health benefits, aesthetic benefits, water purification benefits, all these taken together, that gives a very positive spread of economic calculation, including the socio-economic. So that allows the cities and the governments to invest on this kind of infrastructure. So we lack, in Sri Lanka, we lack this kind of economics, because that's why we are not investing on cycle paths. That's why we are not investing on some of these wetlands. We do only for the walking paths, but the benefits of the same thing is not calculated properly. This is another example, this Sri Lankan study. Now we see the erosion rates from different forest types. You can see dense forest, tons of kilometers squares per annum is 100. And then you have tobacco something, you can see the numbers, the variation. Poorly managed tea. Now but at the same time, if you manage tea, it will be much less. So you see these differences. So this is where you need to use the nature related knowledge. Otherwise, we will continue to have the tanks filled with silt, and the electricity generation capacity will be lower and lower, less water for irrigation, etc. This another one is a seawall. from, I believe, from UK. So it's they tried this seawall business and they couldn't do it because the seawall has to be raised to a huge height to minimize the flood. So they decided to, okay, let the flood come. We'll have a wall to a certain extent, but did the economic calculation and let certain lands get filled with water during the high tides. It worked and the economics were very positive and the benefits also were positive. So some of this is a southern freeway. And the most, the example that we can be very proud is our tank cascade system. There are a lot of research went in. Now, this is the one classic nature-based solution implemented more than 2,000, 3,000 years ago in Sri Lanka, where we use the nature. Example, this tree cover reduces the wind touching the water surface and then keep the water little colder so the evaporation rates are minimal. At the same time, before the water comes into the paddy fields, we call the kattakadua in the scientific term, it absorbs all the salt so that the paddy fields don't get the salt issues and browning and etc. So these are all designed long time ago. And then this cascading system. Now there are studies to say that the water use efficiency in the cascade systems is about 6 times. So you get the rainfall, the same raindrop going from tank to tank. By the time you release it, you have used that same raindrop 6 times. So these are the great nature-based solutions that we can enrich more. Again, by income of countries, you can see nature-based solutions are the green ones being applied more by high-income countries, and other countries that the low end are picking up, and they are using more and more engineering approaches, partly as big borrowings. So UK and the whole EU has done a huge study how we can use the nature-based solutions to meet the climate targets, because the green cover is required to reduce the emissions. Then comes a very important part for us in Sri Lanka, quantifying. Because for that, the knowledge is available. The knowledge is called natural capital accounting, and expanded version is called natural capital assessment and accounting. And that allows us now, if you take a land parcel or a region, you could separately count how much tourism benefits, how much water benefits, how much urban benefits, how much household benefits, and you then add up all that. Then you bring it to the national accounting, that's you call this ecosystem service flow counts. So if you get this, the whole national budget, the investment and the way the parliament do the budget debates will change, because the investments and the benefits, the way we think, will have a different connotation when you apply the ecosystem flow count. So it's something that Sri Lanka badly needs. Otherwise, the land parcels will be wiped out in the name of agriculture or in the name of housing development. But the real value of the ecosystem services provided by that land parcel is not known until it goes under the bulldozer. For example, good example is mangroves. It provides environment for fish to breed, and also it resists the nature's challenges like the sea level and things like that. It provides firewood. It filters a lot of chemicals coming from the land, the ones it released by the cities. Now, for example, if you take the city of Calcutta, they use mangroves as their wastewater treatment system lot. So these things need to be quantified. Now, one of the quantifications done in Sri Lanka, thanks to Professor Prashanthi Gunardana and the group in Sri Jadanapura, we have calculated the pollination benefits, the watershed benefit. This is for the forestry. only for the forestry. But we haven't done it for the coastal or the marine or the other areas. So there are numbers that one can refer. The forestry contribution for recreation, how much, the timber value, how much, mangroves. So like that, now watershed protection benefits. Now, when you add up all that, this is a good way. The pollination, you can see the huge row number 8. Now, you ensure the ecosystem services, and then you ensure the pollination benefits. So these are the things that pharmaceuticals, these are huge numbers. Like, I mean, you could convert the avoided losses and all that. I'm not going to discuss this due to the time constraint, but you could get into the high level of economics. Coming to COVID, as Professor Rupika mentioned, the COVID connection and the zoonotic connection. So that brings us why we should keep the wild animals in the wild and the domestic animals in the domestic front, rather than allowing them to get mixed. So now it has been adopted widely by the World Wildlife Fund and many other agencies, so are getting connected to the nature-based solutions and also to the development efforts. You need a lot of planning to adopt nature-based solutions, because the nature-based solutions also can backfire if you don't adapt it. So you need to do the land use planning properly. And at the same time, we need to monitor all these solutions we are providing, because those will develop social benefits, environmental benefits, economic benefits, but we need to keep track of all that, have the right kind of indicators, and then make use of them in the policy and planning. But having said that, we need to use the adaptive management, because there is nothing is in concrete. There's no right solution. We all learn this. We had to learn, adjust, plan, and then repeat these cycles. Because of that, the IUCN has introduced a global standard for the nature-based solutions. I'm going to, you can type in nature-based solutions global standards. It will come up in the internet. It can be applied to countries. It can be applied to regions, watersheds, and then at any different scales. So we went through a lot of examples and a lot of ideas. Hopefully, it probably had helped to raise a lot of thinking, hopefully. So in summary, the nature-based solutions is an approach to address social issues. It's not just saving the environment, faced by the government and the communities. It could extend from poverty, climate challenges, energy generation, life quality, health, anything. So the NBS, or the nature-based solution, should be based on science and technology, with the proper monitoring to minimize any unintended negative consequences. You don't do a soil band without doing the right analysis. That's what we see here in the Central Expressway in the Gampa area. So the sustainable financing plays a key role in nature-based solution mainstreaming, because you can have solutions, but you need to figure out the sustainable financing. Now, for example, now in Kalana River, we have that high erosion. The only way you can reduce that erosion is restoring the degraded land upstream. So can the Kalambu people who want pure water can contribute through a tax scheme or a sustainable financing scheme, or the people who are in the industrial parks enjoying the good quality water, wanting to enjoy the good quality can. So these financing schemes are required in Sri Lanka, and the innovation is required to design these kind of financial schemes. So in doing so, we need to strengthen the university practitioner collaborations. There's one way to advance the nature-based solutions toward the long-term sustainability and resilience. So thanks for listening, and really again, thanks for inviting me to share a few ideas, and thanks again.
Thank you, Dr. Malvathandri. Well, our next speaker is Professor Suzanne Lenhart. I'm waiting for her to connect. She's connecting from US.
She is
I am
connected.
connected. I am connected.
Hello, Professor Lenhart. Okay. Let me formally introduce Professor Lenhart. Good morning, Professor Lenhart. You are early morning for you, right? And warm welcome to the webinar, and thank you for joining all the way from Knoxville, Tennessee. So we are excited to have you with us today. So Professor Lenhart will be talking about the One Health aspect, connecting humans, animals, and the environment. And Professor Lenhart is a Chancellor's Professor in the Department of Mathematics at the University of Tennessee, USA, and is the Associate Director for Education and Outreach at the National Institute of Mathematical and Biological Synthesis. She's also a member of the University of Tennessee Center for Wildlife Health. She was a part-time member of the research staff at Oak Ridge National Laboratory for 22 years. And Professor Lenhart is an applied mathematician working in partial differential equations, ordinary differential equations, and optimal control. So her current research focuses on population models with applications in infectious diseases, invasive species, and natural resources. Professor Lenhart has authored more than 180 journal articles, as well as 3 books, including Optimal Control Applied to Biological Models and Mathematics for Life Sciences. She's a fellow of the Association for Women in Mathematics and also has served as the president. Also a fellow of the American Mathematical Society, the American Association for the Advancement of Science, and the Society for Industrial and Applied Mathematics. So with that introduction, let me invite Professor Lenhart to deliver her speech. Professor Lenhart.
Good morning or good evening to you.
Good evening.
Good evening.
We should be saying good morning.
Okay, yes. Okay. Anyway, I'm very glad to be here, and I want to thank you very much for this invitation to speak to you today, and also want to thank to the organizing committee, and also to Coca Marika De Silva, who's been connecting with me about giving this talk. And today I'm going to talk to you about the idea of One Health, connecting humans and animals in the environment. And so first, just to give a brief outline and give a brief idea about One Health. One Health is representing the connection between humans, animals, and animals can be generally, interpreted as livestock, domestic and wild, and the environment. And there's many features of the environment, as this previous speaker had talked about. And you want to connect the health of all of these so that the human health is connected with animal health, which is connected to the environment. And so to study health problems, you need to look at teams, multidisciplinary teams, and they can work to improve the health of all of us. And just to think about the connections, this is just one small statistics that 6 out of 10 known infectious diseases in people are spread from animals. And of course, we're in the middle of a coronavirus epidemic here across the world, and we know that it's definitely connected to animals. And then what I'm planning to do today is to give 2 examples, and I'll try to emphasize sort of the background of these, and I'll have some mathematical models, but I'll try to explain the terms so hopefully people can relate to them a bit. One of them is called Lacrosse Virus, and the other one is called Zika, and you're probably pretty familiar with Zika. So here's a big umbrella to give you what.
One moment, Professor Lenhart, we can't see the screen, the projection. Are you showing anything?
Oh,
yeah.
Yes. Okay, let me reshare. You didn't see any of these slides yet.
No, sorry.
Okay, let me redo that. Okay. All right. Okay, let me try it again. Sorry.
We can see you very well.
Well, I know, but okay. All right, let me try this. Can you see that?
Yes, thank you.
Yeah. So when I went to full screen, somehow it wasn't showing. I mean, it looked like it was showing to me, but it wasn't showing. Okay, let me try that. Okay. So anyway, I'm again going to talk about the whole idea of One Health, and again, One Health involves the health of connections of human, animals, and environment. And as I was saying, the statistics of the whole idea is that 6 out of 10 known infectious diseases in people are spread from animals. And so in order to study such problems, you need multidisciplinary teams, and you can improve the health of all. So I'm going to talk about 2 main examples. One is called Lacrosse Virus, and it's a mosquito-borne disease, and I want to talk about that one. And then I'm going to talk about a Zika virus with an application in Brazil. So now you can see the umbrella, and the umbrella here is trying to remind you that there's many, many things connected. You know, you're thinking about individual health, population level health, ecosystems, and environmental health, as the previous speaker was talking about. But there's a lot of course, a variety of issues, human medicine, veterinary medicine. But then you can also think about this as you're trying to think of things you study. Think about ways to study surveillance, ways to study vector control. So the idea is that it can bring a lot of approaches. And so I'm going to talk about that. I'm involved with doing different types of models, and that sometimes the models are connecting humans, animals, and the environment. Sometimes just one aspect, but the idea is if it's possible, one should study all aspects. And so the first example is about a virus called Lacrosse. And this is a paper that was just recently appeared in PLOS One. But what's interesting about this, and this is something that's very common in the United States, is that this started as an undergraduate project. This was a project at an institute called the National Institute for Mathematical and Biological Synthesis, which is this right here, NIMBIOS. But really what happened was there was 3 undergraduates, and they were working with us in the summer. And so this is common in the United States to try to get undergraduates involved in research. And so there was one graduate student, Cameron Cook, that was helping. And then there was Blessy, Brosak, and so there was, and Hannah Reed, they were undergraduate students. We had now excuse me, notice that this is going to be a project that was very connected to data. So some of the other people on here, the last 3 people were involved with data, and particularly Rebecca Trapp-Fischel. It's actually her laboratory that's collecting mosquitoes. So you can see that this is a project in which some group of people, UQuar and Maceo, they were collecting data. So basically people were collecting data and we were using that. And so just to talk a little bit about that. And so I want to give you some background on this virus. So it's called Lacrosse virus. And if you look at this diagram, this is part of the United States. And up here in this part where my cursor, can you see my cursor a little bit? Can people see that?
Yes.
Can you see the yeah, okay.
Yes.
So that's up there, and that's a part of where La Crosse, Wisconsin is located. And so it was actually, this virus was, and this disease was first diagnosed up there. and it was quite a few years ago. But it turns out that as time has developed, the place in the country where you have the most cases and the most serious things is right down in here. So you see that a little bit further down toward the middle of this map is Knoxville, Tennessee. In our area, it's the place where this is the strongest in the country, meaning, and so there have been cases in this in our area. And what can happen is that, you know, if you get this, it's from the bite of a mosquito that has this, carrying this virus, you can get headaches, fever, you can have disorientation, seizures, but then you can even get more problems, neurological problems. And so really what happens in our area is that young children get affected and it starts to affect their brain and they can have encephalitis. So it's a serious problem, but it's most prominent right there in the Knoxville area. So there are researchers collecting in the Knoxville area. And there's 3 main mosquito vectors. And you see here, I tried to put the pictures of the 3 types of mosquitoes. And they're all Aedes mosquitoes, Triceriatus, Alopictus, and Japonicus. So there's 3 main types of mosquitoes that are carrying it in our area. Now let's just remind you a little bit about what happens when you talk about mosquitoes. So the one thing about mosquitoes is that only the female mosquitoes bite, and then the males feed. So when I say bite, they will bite humans or mammals, but only the female mosquitoes are biting to get a blood meal. And the males feed on nectars from plants. So, and it's possible that you know, it may be possible that a female mosquito would transmit this type of virus to the male mosquitoes, but then the male mosquitoes are not biting humans. But what also can happen is the female infected mosquitoes may lay eggs that are infected. So this is called Trans-Ovarial Transmission. And so basically the idea is that, you know, the mosquitoes can pass it on to male mosquitoes, the female mosquitoes can pass it to male mosquitoes, and the female mosquitoes could lay infected eggs. But the interesting part is that humans are dead in host, meaning they cannot transmit the virus to other susceptible hosts. Now, this is quite different if you're used to studying diseases that are like malaria, that are, you know, mosquito-borne diseases. In malaria, you know, in malaria, that a mosquito can bite a human, but then, you know, transmit a pathogen. But then on the other hand, when another mosquito bites that human may give a virus to a different mosquito. So many diseases that are vector-borne, in this case with mosquitoes, the humans are not dead in host. The humans are a part of the transmission, but in this disease, the human are dead in host. So again, since the human are dead in host, how does the infection cycle continue? And it's because that there's sort of reservoirs. Now, what do we mean by reservoir? These are like small mammals. There can be like chipmunks and squirrels. Here's a picture of a squirrel here. So they can be like small mammals, and they can keep the disease going, meaning that, you know, mosquitoes can bite, for example, the squirrel, and can go back and forth. And so, so anyway, the whole thing is that the mosquitoes can get exposed to this virus from small mammals, and then there's a cycle continues. So our goal here was to think about how to model this disease, and so we're going to actually be modeling mosquitoes in this particular model. And we know that the environment affects mosquitoes. In particular, we know that precipitation and temperature affects mosquitoes. And so we'll try to talk a little bit about that. So we're trying to get a data-driven model, and it's going to describe the mosquito population. And it's going to use environmental variables, precipitation and temperature, and it's going to represent the average trapping site in our area. So Knox County, Tennessee, that's where I live. And the experiments that were done, the field work was done collecting mosquitoes and eggs in sites nearby in our county. And this model is the first time that anybody has put a data-driven model and described the spread of this infection through the mosquito population. There have been other models representing mosquitoes related to this, but not actually ones where they had the data about the transmission. So here's some idea. This is a picture here. You can see that this is like a trap hanging on a tree. And this is just to illustrate the type of traps that they had. And these were trapped quite a few years ago, but it took us a while to process. All the mosquitoes had to be processed in the data, and we started working on this a few years later. But they had 8 sites of collecting mosquitoes. And just to explain that, they collected eggs. So in these traps, you can also collect eggs, but then they're also going to collect mosquitoes. And I just want to remind you what's going on with, especially the female mosquitoes. The female mosquitoes can be host seeking. That means that they're going to, they're flying around and they're looking for something to bite to get a blood meal. So they may be looking to bite a squirrel, or they may be looking to bite a human, but they're flying around. Host seeking means they're looking for a host to bite. So that's the word for that. And then the word that you think about, which is called gravid. So gravid is mean that they're flying around and they're looking for a place to put their eggs. And that's going to called oviposit. So they want to lay the eggs, and they have to have usually like some type of water area. Some can be very small, even a small container, but they're flying around looking to deposit their eggs. So they cycle between those. The female mosquitoes, when they are adults, so they are adult mosquitoes, they can cycle around. They go between host seeking and then becoming gravid. And then once they lay the eggs, they go back. So it circles around like a cycle. And just to give you some idea, these are, if we average these out, these are during the summer months. And this is a graph of, these are the average number of mosquitoes caught. So basically, you're going to have an average site. So we had 8 sites and we're averaging them. So you see that's what's happening here. In the middle of the summer, the number of mosquitoes caught was going up. And again, this is like an average site. So meaning that, we had 8 sites and we averaged them. And just to give you an idea of how many, when you start thinking about how often they went out and collecting mosquitoes, there were 850 pools of mosquitoes are tested. Now, when you say tested, not only are they collecting these mosquitoes and counting in the numbers, they also were testing them for the virus. And so now when you say testing them, like if they collect a pool, like if they have, for example, 10 mosquitoes in this particular pool, they don't test them one by one. They put them, they test them all 10 together. They put them together in the test materials. So out of 850 pools, there were 8 positive pools. And so there were 49 mosquitoes that were in the positive pools. And so when you put the mosquitoes in the pool, like, you say, oh, I got, 10 mosquitoes, you don't really know how many of those 10, because they get sort of squashed together. You don't know how many of the 10 actually had the virus. So we assumed in this case that half of those were positive, meaning, so basically if you had 10 mosquitoes, we assume at least half of them were positive. Okay, now when you look at this graph, try to see this graph a little bit. There's these little blue dots. These blue dots are showing some of the pools, the positive pools. And so just giving you an idea about, again, the mosquitoes in these positive pools. So these blue dots, so remember the red ones are average, basically averages. And then the blue ones are from positive pools. Again, positive pools means they have mosquitoes with the virus in it. Now, we actually took weather data. And so we use weather underground data, and we computed 2 things. And this is sort of an important thing to realize, that it's when you start talking about temperature, mosquitoes need some temperature to develop, and usually they need temperature to develop from life stages, because mosquitoes are going to develop from eggs to the the immature life stages, which are like larvae and pupae, and then they can go to become adults. But they need temperature, above a certain threshold. And they need like so much of it per day. They need like so basically we had to make this type of calculation. So it takes the temperature at a certain hour and it sees how high above the threshold it is. So it subtracts this temperature above the threshold. And it has a positive thing here that says only when the temperature is above the threshold do we count the temperature, the contribution of this temperature. This is called degree days. So you're trying to calculate, how much of the day the temperature is above the threshold. So that's one thing that we used in the model. And the other thing is we used precipitation. And we had to get the hourly precipitation, and then we decided to accumulate it. But you'll see when we talk about the model, we have to find out how many days to accumulate. So it's not necessarily just the precipitation, the rainfall today. It may be the rainfall over the last few days because they have to build up some small pools of water. So it's basically what you call accumulated precipitation. And this is just some ideas of what the data looks like for environmental features. The red over here on one side represents the degree days. So you see that it's, can be a little bit higher in the middle, but it does fluctuate. And then over here, there's precipitation. And that's the, in this case, sort of the blue looking. And you can see that that does vary across the summer. And again, this particular picture, the accumulated precipitation goes back 20 days. So I mean, if you say, okay, this is accumulated precipitation today, accumulate it back the 20 days. So I'm just going to tell you sort of a little bit more about the biology underneath this that we built into our model. We have compartments, so we keep track of mosquitoes. So we have a compartment for eggs, immatures, and the two female adult populations. So these are called host-seeking and gravid. I was just explaining host-seeking means they're going out to look for a blood meal, and gravid, these gravid females are going out to lay the eggs. So these are the uninfected population. And so the eggs and the immature can be males and females, but when we talk about host and gravid, those are what the female mosquitoes are doing. So we have to translate into female. And then we have what you call infected populations. And again, these are the same populations, but the small v, there's a subscript here, small v means that they have the virus. Now, what's unusual about this, just to understand this infection, when the mosquitoes have this virus, it doesn't bother the mosquitoes. It doesn't affect their growth or their development. It doesn't bother the mosquitoes. They're just carrying it around, passing it to, small mammals and humans. It doesn't affect anything. Okay, so that's something to understand when we, basically when you start asking about the growth rates or the development rates, it's the same for the, the mosquitoes with the virus and without the virus. But there's some other important things that we need to talk about that really we have to think about, what proportion of the eggs that are laid by an infected mosquito are going to be infected. So we had to figure that out. We also needed to figure out, you have these host-seeking mosquitoes, the mosquitoes flying around, what proportion of them are going to become infected? So they're going to be interacting with small mammals. What proportion of them are going to become infected? So we realized that that's going to be depending on precipitation, because the mosquitoes are going to be flying around looking, looking for, again, they're going to want to get a host, and then they want to lay the eggs next. And again, we talked about the pools. We assume half the mosquitoes in each positive pool infected. And so basically some of the rates in our model depend on degree days and precipitation. So here's a diagram. So if you look at this diagram, you can see I have these boxes: E for eggs, I for immature, H for host-seeking, and G for gravid. And so this is what we call a diagram. And all those arrows on this picture represent the transition between these populations. And so even though you might not be too familiar with mathematical models, you can understand that we have some transition. So basically this arrow here from eggs to immature, this is like a stage structure, a life structure change for the mosquitoes, and it depends on the temperature through the degree days. But when they're flying around to do become in this case host seeking, that transition depends on the degree days and the precipitation. And you say, okay, why do you have two arrows with those? And the reason we have two arrows is so this row here is representing the amount of the proportion of females. So these are the females going on to this compartment, and this lower arrow are the male mosquitoes going to do their own thing, but it's not really affecting this disease because they're going out just to feed on other things. But here we got the host-seeking females and the gravid females, and they cycle around. So this is a cycle around here because mosquitoes become host-seeking, and then they will have eggs, and they want to fly around and deposit the eggs. So they cycle around that. Okay. And so each one of those arrows has an equation, has a term in this equation. So maybe we can just say that all of these on this side are the rates of change of those compartments. And then you can see that we have these transitions. For example, here's a minus sign. Here's this dependence on the degree day. So this is saying these eggs go down here. They leave this compartment. That minus sign says it leaves this compartment and goes down to that compartment. And then you have similar types of things. You see that, you have something leaving the host-seeking compartment, and it shows up down here. So you have this leaving up here. It shows up down here in the gravid department. And then here's some gravid ones that are leaving, and they're going back up. So these terms like cycle around. There are some other terms in here, and some of these are basic death rates. These with the subscripts, the lambdas with the subscript, those are death rates. But again, we use, in this particular model, we use precipitation over the last 20 days, and we use also the degree days. Now, you might say, how did you decide 20 days? We tried different things. So when we did this, in fact, I'll try to explain that next. So we have all these are rates of movement rates of change with respect to time. We tried many days, like 3 days, 5 days, 10 days. We tried, looking at those and putting them into our coefficients and try to see which ones work the best. And that's what I'm trying to say here, that and in fact, even to figure out what type of format to put in, we knew the biology, so we knew which rates were increasing or decreasing, and things like that. We knew that, water, for example, the accumulation of precipitation was good for laying eggs, and it's good for, becoming host seeking. So really what happened was that we tried many different functional forms, like for, you say, how did you decide these functions? For each of these things, we tried like about 10 different forms, and we also had to find the parameters. So again, these are the parameters that depended on the degree days and the precipitation. And again, these are, things about the laying of eggs, the development rate of mosquitoes, the development rate in this particular case of the eggs. But in general, mosquitoes, not just mosquitoes, but all insects, lots of insects, their development rates in general, transition of life stages depends on the temperature. And again, we have the development rates. Here's an even more complicated diagram, which I just want to point out that down here, here's all, I was just discussing a picture like this, but the bottom row here, if you start to think about this bottom row, the bottom row is what's going on with the virus. And so here's an important thing to realize is that you have a connection between these two. You see that there's a connection. This right here is a connection. There's a connection. And so if there's a connection, that means basically when the mosquitoes are, out flying around and they bite, so they might bite, a squirrel, but the point is they may pick up the virus from a squirrel or something else. And so they get transformed between being in the regular part of the model into the model part with the virus. And so this is the whole procedures. And you see that these arrows that drop straight down out of these boxes, The ones that goes, like if you start to see that, they go straight down. The ones that go straight down with the boxes are actually the death rates. So again, we estimated these parameters. We want to point out that also, we had to estimate numerically, and basically it's an idea of sort of adjusting parameters until you get a close fit for the data. And we had to also do these 2 rates, one for infection rate. And that means the infection rate, how many eggs are going to be laid that are infected. And then also the vertical transmission, how the mosquitoes acquire the virus. They had to be estimated. So here's some graphics. Maybe this will help you get a little bit idea, but this is a graphic that shows the numbers of eggs and compared to our model. And when you see this, the one that's the dashed lines with these dashed lines, those are lines connecting the data points, and the other part is the model. So you can see there's some fluctuation, but it's very difficult to get a very good fit. And then over here, this is about the host-seeking mosquitoes. And so you see that, there's some relative error here. We actually calculate the relative error, and the relative error on one of these graphs is 12%, and the other one is about 7%. Also, you can show the simulations. You can show all the compartments. Here's some, again, these are the compartments. We're showing the host-seeking mosquitoes. And also we show down here, these peaks at the bottom here. These were the infected mosquitoes. We show those also. And then again, I'm reminding you that we used environmental data. So really what we did is, again, we were able to build this model and estimate the rates using environmental features, precipitation and temperature. And we were also, able to, illustrate how this virus is maintained in the population. And so we worked with the Tennessee Department of Health and our Knox County Health Department. And we got, some of this data from them and from the persons collecting them. But the idea is that we hope to better inform this. So basically, we're currently working on things connecting with the human case data. And basically, this is going to inform when they should start doing spraying. So they definitely sometimes in certain areas in our county spray for these mosquitoes and trying to keep the virus down. It's important to realize that where you might say, where did they decide to collect the data in the first place? They knew some places where there had been some human cases. And so in those areas is where they put the traps and connected. So anyway, this is work that we've done. And this is actually, this particular one we're talking about is actually the third paper we published in this area. And now we're continuing to think about more about human cases. So I'm about to switch to another topic, and this is about Zika. In particular, it's about Zika in Brazil. And this is because a couple of years ago, and now it's probably 3 years ago, but anyway, a graduate student, Tiago Mialco, came to our institute from Brazil to work with me. And he was working on his PhD dissertation, and we were working in cooperation with his advisor, Dr. Meyer from Brazil. And they wanted to talk about the spread of Zika virus. And so just to remind you that, again, Zika virus is transmitted to humans, and it's really mostly by the Aedes aegypti mosquitoes, but Zika can be transmitted by venereal transmission, sexual relations, and blood transfusions. But this disease is another disease that's a concern about humans, and in particular about children. And children can have neurological problems, and it's gotten, of course, a lot of publicity about that. They're still working on vaccines. They are giving vaccines now, but I think that right now people are still concentrated on coronavirus. They're not thinking about Zika vaccines too much now, but there's, we'll get back to that. Anyway, but again, we're thinking about the whole idea of, it costs to distribute vaccines, and how should you distribute the vaccines? So we were trying to think about to control the distribution of vaccines, and we used a model with partial differential equations, and it's in the state of Brazil. And so here's a picture of the area. We only did one part of Brazil. It's a state called the Rio Grande. So Rio Grande North State. So, and the capital of this state is Natal, over in this area. And that's where this epidemic started. And we'll talk a little bit more about it, but eventually it started here and slowly started to spread across. But later there were two places over here, Massaro and Caco. These are places where somehow it jumped over there, and that's because people probably moved over there. So it's not like it slowly progressed over there. It was like the disease jumped over there. For somebody like moved in over there, like a human traveled over there. So because the mosquitoes weren't going, infected ones going all the way over here. So basically it started to change because of some immigration. And so we built a model with, this case has time and space involved. And now we have humans, and we have susceptible, infected, and recovered humans. And when we say recovered, they could be recovered or they could be vaccinated. So basically recovered here and vaccinated means that they're really immune. And then for mosquitoes, we just have susceptible mosquitoes and infected mosquitoes. And the idea, if you vaccinate for this vaccination gives immunity. And we're controlling the vaccination rate, where to put the vaccination. So here's a diagram. But the different thing here is that this goes the full cycle. So when I think about that, so a mosquito can, so this right here is saying right here, this is saying a mosquito, see this V for mosquito with the vector, mosquito can give the virus to a human. So a mosquito can cause the humans to go from susceptible to infected. But you see on this line up here, an infected human can cause a mosquito to acquire this pathogen. And so it's different than the previous disease, because humans are not dead end hosts. Humans can keep the cycle going. And we put some growth in the mosquitoes, and you'll see that in this model, the sexual transmission was not considered. And I'll try to explain why that is, but it turned out, it seems like for this particular data set, it seemed like the sizes of we estimated the coefficients, and the coefficient for sexual transmission was very low. I mean, it doesn't mean it didn't happen, but it was very low compared to the other types of transmission. And so I don't know if we want to talk about these equations too much, but I'll just say a little bit about these. These are equations that represent changes in time and space. And so these terms here with these T's, these are rates of change of times. These are derivatives. These other terms that you see that have these sort of these triangles, those are in space. So those are movement in space. So you have equations that balance out the movement in time and the movement in space. And then you have these same type of interaction terms, basically where you have a susceptible person interacting with a mosquito that has the virus, and that person then moves out of this class with the minus sign and into this class of infecteds. And so basically you see that we have three equations involving humans and two involving mosquitoes. And this is a type of growth term. So you might say, where's the growth in the humans? We're only going to model a few months. So we're assuming temporarily that the human population is not changing. There's not a lot of births, it's too many births relatively. So we're not worried about the births of the humans. We are worried about the mosquitoes, because the mosquitoes live in a shorter time. There's a funny term here, which is an F, and I want to just point out that this is called a source term. And what that means is I was pointing out that in two locations, somehow humans moved in there that were infected. So we put that in the model, and we knew exactly when it happened because we have the data, and we put so this is like adding somebody into the infected class. We put them in exactly what the data said. And what are we trying to minimize? So we'll try to say that again, but we're minimizing the cost of infecteds so that there's some costs associated with people being infected and administering the vaccine. So there's a cost of infected, and there's cost. So these small c's are standing for cost, and there's cost to that. And so the model will decide where to vaccinate and what level. So we have a vaccination level. Okay. Oops, sorry. All right. And so I won't really go into the background behind this, but there's some mathematics behind how you can decide to find the optimal vaccine rate. And so there's some mathematics. It's sort of a generalization of calculus and finding derivatives. And in this case, we're sort of taking rates of change. And basically, you're thinking that this J here represents your overall goal. It's keeping track of the infecteds and the cost, and the overall goal. You can actually differentiate that map from the rate of infection, which is called, rate of vaccination, which is called, U here, and you can send this over to your goal. So you can take a derivative of rates of change and do that. And so we won't go into this, but there's sort of some background here. Again, through these derivative processes, you can get exact formulas for the vaccination rate. And you can see that the vaccination rate depends on the susceptibles. Maybe I could click back and show that for a second. Just let me point this out one more time. In this picture, you see that here is the vaccination rate. It's removing people out of this equation and putting them down into the immune equation. So it's a vaccination rate. Yeah. And if you see that on the picture, here's my vaccination rate on this particular picture. So it's going to moving people from the S class into the immune class. Okay. And so again, we want to show some pictures of what kind of data we had. Again, it's from a particular state, and we were going to estimate some parameters from that data. And yeah, okay. And again, we're trying to make our predictions close to the data from Brazil. This is a picture representation of the data. So you see here that this is 13 city areas in that state, and this graphic is trying to show, here's the weeks that they were, the epidemiological weeks, and then these are the cities that were involved, and this is the key to what the cities are. Natal in the yellow is where it started, and you see how big it got biggest there, but then it's went to other locations, and so again, you also had to figure out that this is a disease that's underreported, and we had to look in the literature and try to figure out, how. So these are the reported cases, but there are more cases, so we had to take that into account also. Now here's just a graph that shows, sort of how we built this. But if you can see this, Natal, that's where this disease started, and it was starting to spread across. But then you can see these two locations, Massaro and Caquio. This is where it jumped to later. And so we had to, at the appropriate time, we had to put in put in some infected people in these two locations. That means that, judging from the data, people just moved in there because you could see that it was starting to slowly spread, and then all of a sudden it jumps over here and it jumped over here. So that's probably due to people just quickly move in somewhere. And we had to look about the distribution of the people. And so in this whole area, there were about 3 million people. And so we had to estimate, and this is just talking to mosquito experts, how big the mosquito population is. It's a good question, how good it was estimated. But these are where we were starting out. And again, we started out with a small amount of infections in the one main capital city, and then we had that spread across. So, okay. And all right. Then I want to show what happens, and this may be difficult for you to see, but what happens when you do no control. So this is saying after 35 days into the epidemic, And then this is 35 represents that, 52 represents day 52, 70 represents it. So this is a picture of it spreading. And you can see that this is it's a type of density. So it's starting right here. And this is the capital city. And then you see these two other locations that it's starting to go to. So there's these two other locations it went to. Now you can see that, and you have to judge this a little bit, but you see that, this disease is going to get, high. You see these numbers over here. Now this is, it's a density. So it's basically the amount of infected people in a small area. So it's a density. All right. So keep in mind that number was like 4 as a density. So, okay. Now, if you apply control, what does control mean? That you start to apply vaccination. So here you have, on these first 2 rows, you have the infected. So these are infecteds across here, and you see that it's still spreading. But you get over here to the end and say, well, this used to be 4. So this is saying with this particular level of vaccination that we did, the level has been cut in half because the density of infecteds is cut in half from what I had before. And you say, well, what did you do? Well, if you start to look at this, this is where we applied the vaccination. So we went to the main locations. And of course, the computer simulations told us how to do this. But basically, this is the idea, is that these U's represent the vaccination rates. And you can see that you have to do it in these 3 locations. And then nearby the end, you can slow it down. But this gives you an idea. Now, we started the control at different things. You say, why didn't you start at day 0 or day 1? Well, you wouldn't start vaccinating at day 1 because you didn't even know the epidemic was going. So that's what we did. We tried it at different start dates. We started at 35 days and other start dates. In fact, here's a picture to show, that we started it, you could have done it at 35 days later, 52 days later, or maybe 70 days. And these are graphs that may be easier to follow because these are graphs when we integrated across space, sort of total up for example, total up the infected at a certain time across the whole state. And so you can again see that if you look at this, the blue curves means you did no vaccination. And so you get the highest number of infections, and depending on how much vaccination you do, you can lower the infecteds. And then again, it has the mosquitoes. Now you might say, here's the controls over here. Again, this is why we're starting at 35 days or at 52 days or 70 days. So that's the idea. We shifted it. And we can even compare how good we are doing compared to our goal. And this also may be confusing, but basically, you have your goal. Again, the goal represents the cost of infecteds and the cost of doing these vaccinations. And you can compare, you're trying to minimize this cost overall, do the minimization. And so really you can see how much better you do. So basically there's a value of this goal. Start to look at your goal and you want to say, here's the value of your goal with no control and how much better can you do if you do the control. And basically this is the optimal control. You can do, you can basically do 73% better. So anyway, what we did is try to compare these different things about, and so that this chart is showing, how much better you can do if you do start at 35 days, 52 days, or 70 days. And so you can see, what can happen. And again, you have to think about, what you want, but as you change things, you're going to get different results, right? So, and you might say, this is a little bit tricky to compare. It is tricky because if you, the disease is going to be different because if you, did nothing the whole time, that's one thing. But of course, you have something happened to the disease. But if you start, at 35 days or 52 days, you're going to get different results. So we felt like we did a successful mathematical model of this vaccination. And again, we applied it to the data in Brazil. And we have worked on some cases where you do other types of control, like trying to prevent, other things, do actions on humans or on mosquitoes. And again, this can be applied to similar diseases. So I wanted to say that, I'm not just, working on these diseases, but I'm involved with a program that enhances mathematics collaboration within Southern Africa. It's called Masamu. That word means mathematics in South Africa. And this is a project funded by the National Science Foundation of the United States. It's based through Auburn University. But basically, I've been going to Africa. I've been to Africa, 5 times in recent years and we go there and work on mathematics collaborations with researchers and students in Southern Africa. And unfortunately, we didn't go in 2020, and I'm not sure we're going in 2021 either, but we'll hope to go back. But we end up working on a lot of disease models that actually have to do with diseases in Africa. One we worked on is a project called Borrelia Ulcers. That's a type of pathogen that causes big ulcers on the skin, and we use the data from Ghana on that. We've also been involved with modeling and talking about what happened with the contact tracing for Ebola in Sierra Leone. We've recently also worked on some ideas about the stigma of HIV in Kenya and what effect that has. And currently we're working on modeling COVID-19. And as you know, that in South Africa, the vaccination has not really got started too soon yet. So it's just barely getting started. And we're modeling COVID-19 in South Africa. And literally we're doing it near Johannesburg, getting the data from there. And we hope to also do some things about Botswana. But the point is that, I'm interested in, One Health concerns over different parts of the world, and, working with collaborators and working with data and try to make a difference. And I just want to say thank you very much. And here's a picture of one of our visits. So sometimes we actually get to see a few animals when we go to Africa. Anyway, thank you very much. And I'll be ready for questions together with the other speaker.
Thank you, Professor Lenhart, for the enlightening presentation. But this session runs till 5 p.m. So there are questions posted in the chat box, and I will read out the questions in the order that they're posted. So there is this question. I think this is for Dr. Mallavanthandri. We know that the large-scale agricultural practices and application of chemical fertilizer have negative effect on biodiversity, which includes our important pollinators and natural enemies of crops, pests. Is there a way to reduce these negative effects? Can we go back to small-scale eco-friendly agricultural practices? Dr. Mallavanthandri?
Right, I think it's a very good question. The quick answer is like we need to do both. We need to have the large scale agriculture also, and also the small ones. But what we need is what we call precision farming. Like, if you don't know what you do, you can't manage it. Now, for example, what happened in the fertilizer business is we don't treat fertilizer as a drug or a real chemical, partly because it was given as a subsidy. So it's a free thing. So that's why we see the research indicates about 30–40% of the fertilizer applied are leaving the field, raising a lot of off-site effects. So what we need is, if you were to use fertilizer, you do it as a treat respectfully, and then use the required quantity to get the job done, not to pollute the offsite. Then comes the other side of it, which is the one being promoted these days, is the soil quality. Because the fertilizer use efficiency is depend on the quality of the soil, the water retention capacity, cation exchange capacity, the many other properties in a good soil. The healthy soil will promote the fertilizer use efficiency, and it will keep the fertilizer near the root zone, not in the groundwater or in the surface water body. So we need to understand the value of soil quality and then the need to combine the limited amount of fertilizer that are required, because now there's a misnomer in the word organic fertilizer. I think that's total. It was interpreted in a very complex way. Organic amendments are soil quality improvements. They are not. They are giving a little bit of nutrients, but their main role is supporting the plant to absorb nutrients. So there again, the microbial side of the story. You have good soil, the microbial activities and the ability for soil to generate fertilizer, release nutrients, nitrosomonas and other things will be more. So I think the answer is we need to, it requires a change in the way we think also. Rather than this or that, we need to find a way you do precision farming, use the best in both worlds. If you do, I believe our fertilizer consumption can be taken to very low level, because we have taken in a lot of very soluble fertilizer like sulfate of ammonia and urea. It will get dissolved 100% when you put it down in the soil or water. So I think we need to work on those and the crop selection. I think all this, if you work all that, you could do both commercial farming as well as the small ecological farming, and the ecological farming can bring better prices or different market segments. So I think we need to think a little bit more holistically rather than getting bogged into these silos and try to argue like this or that. It is not this or that. It is everything with a good understanding and with science. Thank you.
Thank you, Dr. Malvathandri. And the next question is also, well, it's a kind of a very broad question. I'll read out the question first. What are the actions taken by IUCN to turn around the ecocide currently happening in Sri Lanka? Well, that is another webinar, I suppose, right? I don't think you can answer that in 1 or 2 sentences, but you can give it a try. Have any action been taken?
It's probably an easy one to answer. We do have a mandate. We are a hosted agency by the government of Sri Lanka to support Sri Lanka. So our main role is to generate science and share science and advocate science. So we do that continuously. So we are working with all the key departments and agencies and the universities to give that science knowledge. And this is one of the events that we do. But we sit with, now yesterday morning, I was sitting with the Forest Department, Conservator General. We work with the Wildlife Department, the Coast Conservation and all the likes. But there is a limit, because it's not, our role is not to solve all the problems in Sri Lanka, but to support towards sustainable development. So if somebody expect us to do like picketing and that sort of work, it is not our role. So as a result, we may have our limitations in providing information and doing advocacy, but we do that to the best of our ability.
Yeah, thank you, Dr. Malvathandri. Next is more of a comment. Palugaswara Cascade system has been declared as a World Heritage. Yeah. And then another question, scientists and policymakers have to necessarily carry the community along in order to make these changes a success. Could you please share good practices and interesting examples of successful community education and partnerships from around the world?
Actually, I mean, there are plenty. If you look at, I think today also I cited few examples, but I think if I were to quote one example. One is, I think, Professor Suzanne is also there from Chesapeake Bay. Now, Chesapeake Bay, after New York development, became a very polluted watershed. But everybody got together, brought in science. Now people go to Chesapeake Bay to enjoy crabs, because it's the mentality or the perception got changed from the worst polluted place to the place that you can go and eat shellfish and crabs. Now, okay. Now, how did you do it? I think that's the question. You need the community to understand properly why it is happening. So we called it load-based programming, meaning you quantify what is the load you are adding from power generation, what industry, agriculture, what is the footprint you create from tourism. Then you come together and then set, we call it the maximum daily loading limit. So that kind of an argument, which is again a US term. So then you decide, okay, we need to get to this level, say 2 years down the road or 5 years down the road. First year we do 20% improvement, 30, 40, likewise. So then you provide the knowledge and educate the stakeholders from the government to the community, and then carry the whole program. So when you do that, I think it's very successful. And one of the good examples I can cite is there's a study we were involved immediately after the ending of the war. It's called the Integrated Strategic Environment Assessment for the Northern Province. It was led by Professor Buddhi Marabe in Peradeniya University. So I was the UN team leader. So basically it highlighted the development needs and the conservation needs together, so that you could take certain lands and then put it for development, and certain lands you need to do the conservation to ensure that elephant corridors and all the other services are in. So I think there are plenty of examples I can cite, but most of the examples had good economics calculated by someone who is in the pre-feasibility of that work. So that's where the mangroves restorations and many other forest restorations were possible, because the economics allowed it to go front. But here what we are missing is that part of economics. Thank you.
We can't hear you. Yeah.
Oh, sorry. Next question is to Professor Lenhart. In Sri Lanka, we have seen Aedes albopictus feed on non-human host, the opportunistic feeding. In such situation, is a possibility to transfer those viruses to non-human hosts?
Yeah, that's an interesting question. I know that definitely, non-human hosts will have the virus, just like we were talking about with the squirrels and the mosquitoes. But I know that also in places like India, for example, I've communicated with people that malaria, that you normally think about the human variant of malaria, that somehow it appears that sometimes the elephants now in India are getting human diseases, like in cases like human tuberculosis, for things. Anyway, so basically sometimes there's like human variants of diseases, and now some of these human ones are showing up in other animals like elephants. And the question is, where did they get those? Did they get them from their human, basically their human caretakers? Are they getting them from, anyway, so there's a lot of interesting things to study about the transfer of viruses among humans and mosquitoes and mammals and different types of things. So it's a very interesting, I see that there's also a question there that's about the size of the farms. Basically, people do worry about the size of the farms and how it is to basically try to contain diseases. We've only tried to study that once about containing diseases in certain types of animals, like cows or sometimes even pigs, because somehow the more they mix together, the more they can spread diseases to each other. So yeah, the size of the farms make a difference. Yeah.
All right, thank you, Professor Lenhart. Next, we have a comment from a participant. The FAO has recommended small farms instead of huge farms to minimize the spread of infections. Already many nature-based solutions are being implemented. They need to be scaled up.
Yeah, that was what I was mentioning. I read that one about the farms, but I think you're right that how much the animals interact can have to do with how big the farms are and how many animals like are feeding in the same locations and things like that. So yeah, sometimes I think small farms are definitely can be easier to manage diseases.
Okay. Then there are a couple of questions from a participant. Number one, what are the steps, strategies taken by relevant authorities to promote NBS research in Sri Lankan universities? As academics, although we want to contribute, we find that research funding is very rare in this area. Most of the international funds are given to NGOs in Sri Lanka, not to universities and young mid-career researchers. Number two, can you suggest places where we apply for grants in field of NBS to Dr. Malvathandri?
Right, I think probably Prof. Suzanne can add, but normally in Sri Lankan context, we have set of funding from I think those are the known ones for universities, the National Science Foundation, CARP, and all that. So beyond that, we need to be a little bit more strategic when you want to raise funds. You need to be on the lookout for where the money is. The good part of the NBS is cut across wide spectrum of things, health being one, disaster being the other. Likewise, climate adaptation. So it allows you to work on a broader platform with multiple partners. So what we are experiencing recently is when you want to try to fundraise alone, it's become tougher and tougher. But there are foundations, there are entities who look for partnerships. So if you can come a little bit out of the box and then having partners across the ocean or having partners inside the country with different talents, because some of the issues require us to be, it's not like the paper with the student and the professor. It's a paper with 10 authors coming from different angles that we are talking as more competitive today. So in that context, I believe there are two things one can do. One is look for these partnerships. Other one is look where the money is. Now I can give one example that is very close to the Peradeniya University. Now IUCN wrote a proposal along with the government to Green Climate Fund. It's a $39 million grant which is now approved. Now one of the main partners is the University of Peradeniya. So now the question is how you position your expertise in that kind of scenario. And I remember inviting soil science Professor Dandeniya to one of our projects in Carnelia, because now again, build the relationships, work with the agencies, then I think then you would find more and more opportunities. Global Environment Facility is the other big funder. But those funds are also being handled by agencies like FAO, UNDP. So we need to work with those agencies more and more. So I think for that, the junior researchers in universities has to work, get the professors, and then collectively approach different partners. So I believe there are a lot of success stories inside the university itself, but the potential is enormous if you can be a little bit more innovative. There are the funding for the traditional things are drying out. So you need to be a little bit more innovative. Maybe that the example, the tank restoration, it's a classical thing in Sri Lanka, but partial desiltation is novel. So likewise, you need to come up with, now for example, now we talked about organic agriculture. Now there had been techniques using fish meal and all kind of things to get more tillers in paddy. Now, the government is now pushing money for SMEs to undertake activities. Now, how do you come into the middle? So being in the context and also looking for partnerships, working with agencies closely. Those are the multiple things that you could start inculcating, so that funding is hard. Funding is not easy anymore. And especially funding is now related to the foreign policy as well. So it gets trickier and trickier by the day. So we need to be innovative to go through these hoops. Thank you.
All right, and then there are two questions to Professor Lenhart. I will read out the whole question. Thanks, Professor Lenhart. In the beginning, I thought, what mathematics professor going to do with One Health? However, slowly I have touched with this speak. Very interesting angle of One Health. I'm from the geography department and willing to know the time and the space dynamics of diseases and the influence of mapping technologies as you shown the spread of disease. Professor Lenhart?
Yes. So I agree that basically we don't show it too much in this, but we're definitely working with people that know, geographical tools like GIS and mapping tools. So we are definitely, especially now with coronavirus, we're like, mapping different types of features geographically and using socioeconomic and different features to look at, for example, the places with high risk of coronavirus. And so you're right that it's a good thing to cooperate with people that have, geographic skills. So that's really important to, bring together different parts of a team. And so, yeah, a lot of my students currently are learning mapping skills and taking classes in GIS. So, yeah.
All right, and next question is, I would like to clarify the data you use for host-seeking adults. Are these the number of females attracted to traps?
Yeah, so basically the females are the ones mostly flying around who are, looking for hosts. So yeah, we're capturing a lot of female mosquitoes in those traps, exactly.
All right, thank you very much, Professor Lenhart. So let me check the chat box once again. Okay, there's another question in the chat box. Is there any opportunity for all actors to come on board and test some of these excellent NBS in Sri Lanka and support development process? Question to Dr. Malvathandri, I guess.
Of course, I think there are a couple of, there are opportunities. Of course, I can talk about IUCN. Now, IUCN have large projects. Yeah, we are mostly welcome to come and check with us. And there are people who graduate from University of Peradeniya who are also in our staff. Now, one example is in Mallathuya Basin. Now, we are having a project called Managing Together. Managing Together is multi-sector, multi-stakeholders. Stakeholders are also private, government, NGOs, and communities. So that kind of scenario allows us to do a lot of nature-based solutions in there. So that starting from Anuradhapura ending up in the ocean with seagrass and dugong. So I think I can extend that to anyone who would like to work with us. And beyond that, there are other projects in Sri Lanka. Now, I mentioned about this Green Climate Fund project, which is coming on Knuckles, and it extends from Knuckles to Anuradhapura area. So already the initial work is starting, and some of the University of Peradeniya staff are involved. But those projects need different angles. Now, most of the time what you do is like you work with the hydraulics and the natural resources. But there's a huge element on the health side, the social science side, and psychology, traditional knowledge. So those things has to be, there are a lot of room for modeling those on top of the hardcore irrigation jobs or cultivation jobs. So, and also the value additions, the packaging, the waste reduction, the the high-end markets. Now, one example is now we were having a project in Derived Island, and the people were selling dry fish. But the way the dry fish was done was putting a lot of salt. But the moment you reduce the salt content, the dry fish is very appealing for people with hypertension. But there are people living abroad who love to have that kind of product. So there are a lot of innovative products that can be developed using Sri Lankan material. So I think the options are, we warmly welcome anyone who wants to contact IUCN. I think we are welcome, but there are many other agencies in Sri Lanka. You need to be aware and look around. Thank you.
Thank you, Dr. Malvathandri. And now we have to wrap up the session. It's 5 o'clock. So let me formally thank once again Professor Suzanne Lenhart and Dr. Ananda Malvathandri for sharing their insightful information with us. Let me transfer the control to Professor Inoka Karunaratne to wrap up the webinar.
Okay, thank you very much, Professor Rupika, and I really thank Professor Ananda Mallawatantri and Professor Suzanne Lenhart, the two speakers who gave speeches today. So they were really interesting, and we had a very successful Q&A session. So on behalf of the University and iPURSE committee, I again thank you all the participants, those who joined the webinar from all parts of the world. Okay, so this is the time for us to adjourn the webinar. Okay, thank you.